All right, so last time we left off with this idea of, this new future value formula, which is essentially kind of like the compound interest formula, but on steroids, right? So you have this concept of compound interest, which kind of keeps a pretty basic formula, right? The one that we looked at the beginning of of the of the lesson. And so you had these kind of four main criteria based on, depending on how much I deposited, depending on how many times it would compound, whether it was weekly, monthly, semi-annually, quarterly, or daily. That would represent your compound level, then your rate, right, your percentage, and then the time in years, right? But then we ran into a certain problem where we had a situation where this particular person was not only investing an initial amount, but then every month or every quarter, they were also depositing another amount, right? And so then we kind of evolved into this new formula, which is right over here, right? Which is the future value formula with the recurring deposit, right? And then we took a look at, well, how does it change? And the big thing is that now we have I and A, which represent two different things. I would be the initial deposit, right? The amount of money that you put into the account at the very beginning when you first open it. And then A would then start to represent the new amount of money that gets deposited every period, right? So when I say period, it could be like every week or every month or every year, right? Depending on what type of account that they have. Okay, the rate, obviously, that doesn't change, and neither does the time, right? But now this takes into account how much money you can look forward to if you continue this kind of like strategy and this pattern moving forward, right? So then we looked at an example of this girl whose parents had been saving money for about 10 years. And what we had in that situation was that the girl's parents deposited 600 every quarter. I think actually no, for her it was every year, I believe. But the initial deposit was only 400, right? So you see the two different quantities there. Inside everything else, right? You have one plus. This would have been your rate, right? The rate per year, right? Shows up multiple times, and then you had the time, which was 10. So it was the course of 10 years. Okay. And so then what we did was we found this value using our formula, and then we compared it to the value that we would have gotten or that we got when we were doing the spreadsheet. Sorry, let me close my door. All right. So what we end up getting here is essentially they are the same amount. They're off by very small decimal numbers, but it doesn't even it's not enough to affect it. So what we see here is that we have a pretty accurate formula that we can use whenever we have a scenario that comes up where we have a person that initially deposits something, but then every compound period they keep depositing money. All right. Any questions about that so far? All right. Okay. So then here's what I want to go to next. So we basically answered on number 4, right? We took a look at explaining the pattern of the reasoning, right? So we looked at what do the variables I, A, R, and T represent in the situation, right? So that's the same formula that we just looked at. Okay, we also used the formula to find out what the future value in her account would be after 10 years. Okay, so now just to kind of warm us back up, right, to take a look at what would be the amount of money in her account after 18 years. Okay, so let's go ahead and just work this one through. Sorry, I'm gonna detach for a little bit to get my tablet. Okay. All right, so real quick, let's just kind of copy this formula over one more time. So this is still part of 4C. So you have F, which is final value, is equal to I, which is your initial, times 1 plus the rate to the power of t, plus A, which is the recurring deposit, times, here you have a ratio of 1 plus the rate to the t power minus 1 all over your rate. Okay, and so there's a couple things here that they are assuming that we know already because they were talking about problem number 2. And then problem number 2, if we go back to that real quick, it actually doesn't show us. I guess it does. Yeah, so we have the information right here, right? We can see that the initial deposit was 400. We can see that the recurring deposit was 600. We can see that the interest rate right here, they've already converted that to a decimal for us. And I believe that's all we need, right? And then obviously we know that this is over the course of 18 years. All right, so we can go ahead and substitute these values in, and then we can go ahead and figure out what that balance is going to be. Okay, so for F is equal to, we have I is going to be the initial deposit, right? So I for initial, so we can use 400, 1 plus the rate, it's already in decimal form, so we can go ahead and use 0.032. And now to the T, this is after 18 years, right? So 18, assuming that, right, she goes to college after 18 years or so, plus A, which is now the recurring deposit, okay? So then that represents the 600. So we would have 600 times 1 plus the rate, which is 0.032 to the 18th power, minus 1, and then this all over 0.032. Okay. All right. Is that okay so far? Does it make sense where we got all of the pieces of information?
Yeah.
Yeah, we're good. Okay. All right. So now from here, then it just requires a little bit of calculator work, right? So we can clean up a little bit. This would be 400 times 1.032 to the 18th plus 600 to the 1.032 to the 18th power minus 1 all over 0.032. Okay. All right. So let's go ahead and figure out what these values are going to give us. Okay, so 1.032, take that to the 18th power first. Remember that the exponent takes priority over the multiplication. So to the 18th power, right? That gives us this really long number, right, in terms of a decimal. So don't round that off yet. Just multiply this, what you have, by the 400. Okay. So this, we can go ahead and try to round off a little bit. We can go ahead and say, all right, this part gives us 705 points. We'll go ahead and call it 0.17. Okay. All right. Plus, now let's go ahead and see if we can clean up the other side. So starting from inside of the parentheses, right, let's start with the numerator first. So there, once again, we have 1.032. We take this to the 18th power. Okay. Once again, don't round that off yet. If you round too early, it creates mistakes later on in the problem. So leave it as like that for now. From that, you would have to subtract 1. So subtract 1. Okay. And then this decimal, we divide by the 0.032. Okay, so it looks like 23.84, right? Now that is the value for everything that is considered inside of the parentheses, right? So finally, now we just multiply that by 600. And then that tells us there 14,304 with, we'll call that 89. We'll round it up to 0.90. Okay, so 14,304. Okay. All right. Any questions on that part so far, like the calculation and the calculator stuff? We okay so far?
Yeah, we're good.
We're good?
Yeah, we're good.
All right. Cool, cool. Okay, so then now we just go ahead and add up these two quantities. 705.17 plus 14304.90. And we're looking at $15,010. Oops, with 7 cents, I think. Yeah. Okay. So just a quick recap there about the difference, right, between what she could get um, or what her family could get if they waited a couple more years, right? So from 10 years, right, if they save for 10 years, it's 7,490. They save for 18 years, it basically doubles, right, up to about 15,000. Okay. All right. All right. Okay, so then part D is essentially asking us to do this again. So this would probably be one of those questions in class where I'd probably have you do it on your own. But in this case, we'll just kind of talk about what needs to be done um, rather than having to go through the calculation all over again. So suppose Lucy is considering joining the Peace Corps and delaying college enrollment for 2 years, right? So this is under the assumption, right, that from the time you're born and the time you start college, it's about 18 years, right? So that's why we're using 18 for this particular problem, right? 18 years up until she graduates high school. But she wants to delay college enrollment for 2 years, right? So then if her parents decide to extend their investment for those 2 years, they're going to keep investing, right, from year 18 to year 19, and then from year 19 to year 20, right? So then after the additional 2 years, what will be the future value of the investment? Okay, so really the only thing that changes is if we were to set up this problem one more time, is that instead of investing for 18 years, well, the 18 years plus an additional 2 years, now we're talking about 20 years worth of savings that can then be applied towards college tuition or whatever, or however they want to spend that. Right. So really the only thing that changes is for part D is just to change the time from 18 to 20. Right. And you can see that because it's just a delayed, right? It's just delaying college for 2 more years. So you would have the similar setup of 400 times 1.032, right? The rate hasn't changed. We just have a different time, okay? Plus 600 times 1.032 to the 20th power minus 1 all over 0.032. Okay. And then if we were to go ahead and calculate that through, let me go ahead and just give you what the approximate value is. Here, what we would find is that the final value reaches 17,205 with 28 cents. Okay, so a couple more years, a couple extra thousands of dollars. Okay, so it's not growing by much. You can tell that here what's causing this to grow really is the recurring, right? Each year they put $600 into the account. So the investment helps it grow, but because of the percentage is so low, right, at 3.2%, you're not seeing huge growth beyond whatever the person is investing, right? Obviously, it's essentially kind of like free money to yourself because you didn't really work for it. You just put it into the account. But you would probably expect that if you saved for 20 years, you might have a little bit more than $17,000, right? It doesn't seem like a whole lot. And that's in terms of reality, that might pay for like 1 or 2 years worth of college, but maybe not all 4 years. Okay, so just to kind of put it into a little bit of context. All right. Okay, Any questions on 4? Are we good on that one?
Yeah.
Yeah. All right, cool. Okay, so let's go ahead and move on to number 5. So number 5 kind of builds off of number 4, but it has us look at it a little bit in reverse. So we're gonna do a little bit of like solving equations. We're gonna use a little bit of log. All right. So for number 5, first thing here that we're told is that suppose Lucy needs 20,000 for the cost of attending her local community college. Okay, so how many annual deposits are needed for her parents? Oh, I'm sorry. How many annual deposits are needed before her parents have saved enough money to cover her college costs? Okay, so check your answer using the formula in problem 4. Okay, so we have a hint there, right? Obviously, Lucy is the same girl from problem 4 and the same girl from problem 2. Okay, so we're just reutilizing all of this information over and over. Okay, so going back to number 5, the key thing is that now we have a goal, right? This is what she needs. And so far, you can tell that even if the parents would have saved for 20 years, they wouldn't have reached that goal, right? Because they would have been short about $3,000. So then what we need to look at is find out how many years do they really need to save before they can actually afford to send her. And then that can give us a more precise number of years for which they need to save. Okay, so use the formula in problem 4. Okay, so let's go ahead and use it. So we know that that would be represented by f equaling the initial value times 1 plus the rate to the power of time plus the recurring deposit, which is a times 1 plus the rate to the power of time minus 1 all over the rate. Okay. All right. So now the question is asking how many annual deposits. How many annual deposits? It's not asking what the deposit should be. Okay, so that has to be kind of clarified because we're not looking to solve for how much money should they put annually. It's how many years, right? How many times do I have to put this deposit into this account to then get to 20,000, right? It's not like should I change my annual deposit to more than 600. Okay, so that is clear. That needs to be clear because what we're solving for here is time. Right, we're solving for, whoa, I don't want that. We're solving for t, okay? Not solving for a, all right? So let's plug in every piece of information that we know, right? So we know that the initial amount, and I'll kind of write it off here to the side so we keep track. The initial amount of money that was invested was 400. The recurring amount every year is still 600. The rate at which she is getting interest on her balance is 3.2%. I'm just going to go ahead and write it as the decimal, which is 0.32. And then time is what we don't know, right? We don't know how long it's going to take for them to reach 20,000. Okay. All right. So let's plug everything in. And then obviously we have another variable here to work with, which is final value. And we're actually told what the final value is because they told us the goal, right? So we should use 20,000 as our F because that's what we're trying to get to. So 20,000 here is the new addition as a piece of information. Okay. Does that make sense where I got all of that information from and why we're solving for T versus why we're instead of solving for A?
Yeah.
Yeah. Okay. All right. So let's plug everything in. And so here we go. We got 20,000 is equal to I of 400 times 1 plus the rate. The rate is 0.032. I'm just going to go ahead and write the full answer here, which is 1.032. I don't know T, so leave T. Plus A, which is 600, times, here we have 1.032. Again, we have time minus 1 all over the rate of 0.032. Okay, All right, so then here's what's going to get a little bit tricky. It's going to require quite a lot of use of algebra. So the idea here is to solve for t. Now, the problem that I have right now is that I have t in two separate locations. If you ever want to solve for a variable, the variable needs to be kind of like brought together in the same way that if you were solving an equation similar to 5 equals 3x plus 6 plus 5x, right? The goal in this situation would be to first combine like terms, right? So that you kind of condense, you bring the coefficients together and you really only have the one variable x. You don't want two separate variables like we have in our problem. So we have to manipulate this equation a little bit and try to solve for the parts that we know first so that we can condense it, bring the t's together. Okay, so one way to do that, and the best way for now probably would be, let's go ahead and kind of break this part open by utilizing the 600 and the 0.032. Okay, if you think about what this is saying, okay, this also could be represented as 600 divided by 0.032 times whatever is in this numerator, which is 1.032t minus 1. Okay, I could also think of it this way. It's the same, right? Because if I were to multiply things across, that 0.032 acts as a denominator. So if I were to make it the denominator of the 600 first, it also works for us. Okay, so why do I want to do that? Because then I can actually eliminate some of this information that makes it difficult to get into that t. All right, so let's start with that. So we have 600 divided by 0.032. Let's see what we get here. All right, and then luckily for us, that gave us a nice integer, which is, whoops, sorry, 18,750. Okay, so here we get 18,750 times 1.032 to the power of t minus 1. And now I'm going to bring down the rest, which is 400 times 1.032 to the t plus, and then bring down the 20,000. Okay. Are you guys with me so far with that manipulation and how we got the 18,750?
Yeah.
Yeah, okay. All right. Okay, so then the thing that you might be tempted to do is probably like distribute 400, and then that wouldn't work because again, this t takes priority, right? It's the exponent, and because we don't know what the number of that exponent is, you can't distribute the 400. However, on this side, okay, there is something that I'm gonna do, okay, which looks like you're contradicting, like I'm contradicting myself, but I'm not. Okay, what I'm trying to do here is I want to distribute this 18,750 into this expression, because if you notice inside of this parentheses, there's actually two different terms. And while one of them is protected by a power, right, which means that I cannot literally multiply 18,750 with the 1.032, what I can do is this. I can say that if I were to distribute this, I would have 18,750 times 1.032 to the power of t, right? So notice how I didn't yet multiply the 18,750 with the 1.032, right? It's a product, but it's still separate terms. And then that allows me to also distribute to the far end of 18,750 times a negative 1. So that's just negative 18,750. Okay. If I bring down now this 400, 1.032 to the power of t, okay? Notice now I have something here that looks very similar to each other. Both of these terms have a power of t, okay? And then they also have the same base of 1.032, okay? Now, I don't know if you remember this, but going back to Algebra 2, and let's say, for example, that you had something like 5a to the second power plus, let's call this 10a to the second power, right? When you have the same base, which we would have here, and you have the same power, which we do here, what are you allowed to do? How can we combine these expressions into one? You see how we could take these coefficients, 5 and 10, and add them up? And you would get 15a squared. Okay, I'm trying to show you how it's very similar to what we have in front of us here, because what I have is a 400 as my coefficient and an 18,750 as a coefficient, but my bases, the base of 1.032, they're the same, as well as they have the same power, right? So when you have those conditions of the same base with the same power, what you're allowed to do is add these two coefficients together. Okay, so this is what we were trying to do the whole time, is to bring those two different variables, the two different t's, to bring them together as one expression. So now what we can say instead is, well, 400 plus 18,750, let's double check what that is. That's going to give us 19,150, okay? But they still have the same base with the same variable. So it's still times 1.032 to the power of t, and then I can bring down the rest. Okay, are you guys with me so far?
Yeah.
Yeah. Alice, Katya, you guys okay?
Yes.
Yes? All right. All right, let me know again. Just let me know if something doesn't quite make sense and we can go over it. All right, so from here, right now it's set up in a way where we can do something, okay? We can actually do something now. So we want to try to isolate the t, right? So before we do anything, let's first add 18,750 to both sides. Right, gonna cancel from this side. Now you've isolated somewhat, you've isolated the expression that has the t. And then on this side, this is gonna give us 38,750. Okay, we wanna solve for t, right? So again, the whole process is try to eliminate everything as much as possible to get t by itself. Okay, so what we can do now is, well, let's divide both sides, right? Because we have a product here, and it's not like we can distribute the 19,000 inside of those parentheses anyway, so divide both sides by 19,150. Okay, that's going to cancel for us, and we are left with 1.032 to the power of t is equal to, and then over here, let's see what we get. 38,750 divided by 19,150. All right, so that gives us 2.02, let's go 2.0235. Okay. All right. And then this is where we get to use what tool? What tool allows us to solve for variables that are in the exponent?
Log.
Yeah, we got to use a log here. Okay, so we apply the log to both sides now. Okay, apply a log, apply a log. So now what you have is the log of 2.0235 equal to, when you apply the log on the right side, what do you get to do with t?
Bring it down, huh?
Yeah, bring it down, right? So you bring it down essentially to the front. So you leave it as t times log of 1.032. Okay. So now you got to think of log of 1.032. That right there is a number. Okay. So in order to get t by itself, you divide both sides by log of 1.032 to both sides, right? So here, this cancels. You're left with t equal to, and then here's where we have to use a calculator. So I have log, oh wait, let me use Desmos. I don't like this calculator. Okay, so log of 2 point, I can't type it in. Okay, let's try this. 2.0235. Oh, too many zeros. Okay, divided by, let's go find log again. The log of 1.032. Okay, so what we're getting here is it's 22.37. Okay, so let's close out 22.37. Okay, so approximately a little over 22 years, right? So, but because they're only making payments every year, right? It doesn't make sense that, well, I guess it does make sense, that they'll reach their goal a little bit after the 22nd year. All right, so 0.3 of a year, it's about a third of a year, so maybe about 4 months. So maybe around April, right? So this gives us a pretty good estimate about when they'll reach their goal. Okay. Okay, how was that? That was kind of a challenging problem for sure. But at least it's more fun than just like plugging numbers in. Okay, are there any questions on that one?
Nope.
We're good?
Yeah.
Yo, okay. All right. Okay, all right, so let's see. All right, so that was part A. Cool. All right, let's see what we can do for part B. All right, so how much money should Lucy's parents invest for each payment after the initial deposit if they plan to save for only 18 years? Okay, so after reading this, right, kind of read it to yourself. Think about what variable we're gonna solve for now.
A?
Which one?
A?
Yeah, this time we are looking for A, right? Because not only are they telling us that they're gonna save for 18 years, that means that they're giving us the time, right? They're telling us that they are still going to invest after the initial payment. So obviously the initial is the 400. There's no mention about the rate changing, right? So then that leaves only one option of the A, right? So how much money should they invest for each payment, right? So each yearly payment, what should they invest so that they really only save for 18 years instead of having to save for 20, 22 years? Okay, so for B, kind of a similar setup. Right, so let's go here. Obviously, we still start with this general formula. Okay, and we have everything we need, but we know that what we're solving for is going to be A this time, right? So the final value, they're still trying to get to that goal of $20,000. The initial is still going to be 400. The rate hasn't changed. It's still going to be at 0.032. The time, we know that for sure that's going to be 18 years. And that's it, right? And A is what we're going to need to find. Okay, so how much should they invest on a regular basis? Okay, in this case, every year. All right, so let's set up. Let's see. I don't know if we're going to need log this time. I don't think we will, because we're going to plug in a number for T. So this should be a little bit easier. So final value is 20,000. The initial is 400. Okay, we know that 1 plus the rate, it would be 1.032. This time we know T, so we can go ahead and plug it in as 18. Plus, A is what we're going to solve for, so leave it as A. and then the rest we can substitute. So here we would get 1.032 to the 18th power minus 1 all over 0.032. All right, so let's try to clean up as much as possible. Let's bring down 20,000. Here, let's see what we get when we multiply all this through. So starting with 400 times 1.032 to the 18th power. And then times 400. Okay, so that'll give us 705 with 17 cents. Plus A, right? We don't know what that's going to be, but we can still simplify whatever's going on inside that parenthesis. All right, so let's go ahead and do that. 1.032 to the 18th power. Remember not to round yet. You want to subtract 1, and then you want to divide by 0.032. So here for the product A times this number here, let's go ahead and round this off to 23.84. I guess we could do 841. Yeah, we'll do 841. Okay. All right, so much more doable, right? Because A is not a power. A is just a regular variable, just like X. Okay, so from here, we can go ahead and solve for A by first. Let me rewrite this just because I don't like the way it looks. I'm gonna move this 23.841 to the front times A, okay. All right, so from there, go ahead and subtract 705.17 from both sides. So 20,000 minus 705.17 is 19,294 with 83 cents. And that is equal to 23.841 times A. Okay, so if we want to get A by itself, no need for log, we just divide by 23.841. And A is going to equal for us $809 with let's just say 32 cents. Okay, so that right there represents the amount of money that they need to invest on a yearly basis. So they need to increase their yearly deposit from $600 up to $809 with 32 cents so that they can reach their $20,000 goal after 18 years. Okay, so it does require a little bit of a larger investment, but I mean, probably doable, right? $200 over the course of a year, right? If you're working regularly, probably is pretty doable. Okay. Any questions on that one?
No.
No, a little bit easier, right? Not as bad. Okay. All right, we're doing all right so far?
Yeah.
Yeah.
Cool. Okay. All right, and then let's see what part C is all about. Okay, so now let's see what's being changed. Lucy's parents invest the same amount at her birth and annually on her birthday for 18 years in a savings account with an annual percentage yield of 1.4%. Okay. Make a prediction for the amount of each deposit to achieve the needed amount of 20,000. Okay, so let's kind of dissect what's happening here. So Lucy's parents invest the same amount at her birth, okay, and annually, okay, for 18 years. Okay, so what does that tell you there? What does that tell you about I and A? Or first of all, do we know what I or A is at this point?
They're gonna be the same, no?
Yeah, they would have to be the same. Yeah, we just don't know what it is, right? Because here it's asking us to make a prediction for the amount of each deposit to achieve, right? So if we need to estimate or find out what the amount of the deposit it has to be for them to get 20,000 after 18 years at this new percentage, then that amount for each deposit is also going to represent the amount that they put in at her birth. Okay, so we're going to need to neutralize the fact that I and A are different. In this case, they're going to keep it the same. Whatever they invest at her birth, they're going to keep investing that every year. And then hopefully, right, with this new percentage, it'll get there. Okay, so let's find out. So in order to set that up, right, for part C, final value formula. Okay, what we've established here is, well, first of all, we have a new rate of 1.4%. Now, 1.4% compared to what we were working with is a bit of a drop because the old percentage was 3.2%. Okay, so the rate has dropped. So that should indicate a couple things, right? Like if your interest rate drops at what you're going to be able to earn, it's either going to take you longer to get where you want to go, or you're going to have to invest more to be able to reach it within the same amount of time. Okay, so that's one thing. Okay, so that's one thing to consider. The other thing is the time. Now we know that it's for sure 18 years, right? They told us that in the problem. And then they're telling us that whatever they invest at birth is going to be the same as their yearly deposit. Okay, so then if the investment at birth is equal to I and the yearly deposit is equal to A, well, then basically what we're saying is that I has to equal A. Okay, now what does that mean for us in terms of this formula? Then that means we get to decide here. Basically, do we want to change both of them to I's or both of them to A's? Let's go back to the question to see what they really want us to find. Make a prediction for the amount of each deposit to achieve. Okay, so for each deposit, okay, so I guess if I'm thinking of deposit and I'm thinking of it kind of like happening every year, I'm probably going to then just switch both of these to A. Okay, so really what we have is, instead of having two different values, what we have is just A shows up here again. Okay, does that make sense?
Yeah, that makes sense.
Yeah, okay, because this initial value won't represent for the yearly deposit. So we might as well run it as the same variable because it helps us then bring this together. Okay, so what we're looking for, because we still know that the final value has to ultimately reach the 20,000. We know that the thing that we're solving for is going to be A. Okay, we got to solve for A. All right, so let's go ahead. Let's plug everything in, and let's see where this takes us. Okay, so final value, we know that that's the 20,000. A, we don't know. We're going to solve for it, but we do know this part, right? This is 1 plus the rate. In this case, my rate, because we changed it to 1.4%, now this as a decimal will be 0.014. Okay, so if you add that plus 1, it'll be 1.014. To the power of t, we know it's to the 18th. Okay, plus, again, we have A, something that we need to look for. 1 plus the rate, let me just write it as 1.014 to the 18th power minus 1 all over our new rate, which is 0.014. Okay, all right, so again, looks ugly, looks messy, but luckily we don't need to use log because the power is a number, right? So we can go ahead and just try to clean it up as much as possible, combine some like terms later to combine the A's, and then we solve for A. Okay, So what I would do first here is let's go ahead and clean up the 1.014 to the 18th power. Let's see what we get. All right, so we're gonna have to round this off a little bit. So let's see, let's try to put this at 1.284. Yeah, let's try 1.284, that should be fine. Okay, so 1.284 times A plus, and now we do the same thing to this this expression inside the parentheses. We'll take 1.014 to the 18th power. Oh wait, messed up. Okay, don't round at this point, subtract a 1 instead, and then divide it by your decimal 0.014. All right, so we've kind of settled off here at 20.310. I guess you could round that up to 20.311. So 20.311A. Okay, and then that equal to 20,000. All right, so now let's combine, right? You have these two variables here. They both have A, so you can go ahead and combine these two coefficients. So when we do that, that'll be 20.311 plus 1.284. So that gives us 21,595 A, and then that equal to 20,000. Okay, so now to solve for A, let's divide. And what we get here would be $926 with 14 cents. Okay, so if the recurring deposit that we need to place into the account every year is $926.14, and we also knew that A was equal to the initial investment, then obviously the initial investment would also have to be $926.14. Okay, so whatever they invest at birth, they have to keep investing every year in order to reach that goal. And you notice how the initial investment and the recurring investment, they're much higher than what we got in the previous problems, and it had to do with the rate. Okay, the interest rate was not high enough to be earning money for them, that they themselves had to put the money into the account. Okay, and so that's usually what happens just with bank accounts in general. The lower the interest rate, basically you don't see as much gain in your money as the years go by. So you really want to pick something, if you get a chance, you want to pick something that will give you the opportunity to earn a little more money. So interest rates at like 1%, they don't do a whole lot for you. Okay. All right. Okay, so I think I'm gonna go ahead and stop it here for today. I think we covered quite a lot, and we definitely got pretty comfortable with this formula. So I think then on Thursday, what we'll take a look at is we'll try to finish up a couple more problems, and we'll see where that takes us.